Hello, everyone. And today I'm going to talk about the pathway to generalist robot, a scaling law, data flywheel, and a human-like embodiment. So as robot learning researchers, I think we have collectively made a lot of progress in building specialist robotic system. And this system has shown amazing, sometimes human-level performances in narrow domains. But we still seem far from the dream of general-purpose robot that can perform everyday tasks in natural environment and constantly adapt and learn new skills. I would call this ultimate form of generalist robot as a specializing generalist. By that, I mean they are not jacks of all trades, master of none. Instead, they have a set of core competencies. And also, they are always constantly learning to acquire deep expertise in new domains and new tasks. So on our pathway towards this general purpose robot, I argue that we need to build generalist robot model that operate on open-ended objective and trained on massive training data. So the reason that I see this pathway is that it reflects a common pattern of technological advancement throughout history. So let's take a steam engine as an example. So if you look at the early version of steam-powered machines, so usually there were purpose-built solutions that only work in narrow conditions, whereas they were developed in different civilizations through many centuries. And then in 1764, James Watt makes some important improvement over the previous design. So if we look back in history, his design doesn't have to be revolutionary, but it is practical and effective enough as a generalist approach for widespread deployment. So people start to put it in cars, in locomotives, in factories. And in fact, like the widespread adoption of steam engine is become the hallmark of the first industrial revolution. New industry were created, a lot of new technical problems need to be solved. And so from there, it leads to a paradigm shift of understanding of different energy sources, and that further accelerate the specialization of energy solutions. And now we look at that, and we have much better specialist solutions for cars, for ships, for airplanes. And so they each have their own unique strengths for their own problem settings. And history is now repeating itself in the neighboring field of AI. If we look at like natural language processing, so the earlier NLP models focus on some specific tasks, such as parsing, analysis, text summarization, information extraction. And the recent development of large language models show us that we can actually build a generalist NLP model by training on internet-scale text data. So this language model are not trained to solve a tailored towards solving a particular task, but through massive multitask training, they have a general understanding of human language and word knowledge. And as a result, we can see that we can use them to solve a variety of problems, right? So they can do creative writing, they can write Japanese haiku, they can be a coding assistant to auto-complete your source code, and they can even give you a suggestion for a next trip or vacation. So if we think about solving any of these particular problems from scratch, it's an incredibly hard technical challenge. But by having this generalist language model, that allows us to build much better specialist solutions. So inspired by this, my group focused on building methods and principles to enable and creating such a generalist robot model. So I believe that success depends on the trinity of three key elements: powerful algorithm, massive training data, and a versatile hardware. Right? Today, I'm going to just give you a brief overview of our research along these three dimensions. For algorithm, we focus on scaling our model scaling. That is, how can we train powerful robot learning algorithm whose capability and generalization power scale with data and compute? So there are two key ideas we are exploring for model scaling. The first is using skills as APIs, that we want to build a library of sensory motor skills as the building blocks to scaffold long-term robotic behavior. And once we have the skill APIs, we can now compose them together. We build algorithms to compose them to solve various tasks. In particular, we're interested in massively multitask models whose generation power kind of scale with increasing amount of data and compute. So this is largely inspired by the scaling law results for neural language models. So for skill learning, we develop a new model architecture and training algorithms for data efficient skill learning. So in this work, Viola, we incorporate object-centric priors for the policy design. We first use a pre-trained large vision model to generate object bounding box. So they capture the general object locations in the environment. And then from this object bounding box, we extract some object-centric representation that capture their object appearance and the spatial locations. And then we can use a transformer architecture to encourage the policy to pay attention to task-relevant objects and reason about their relationships. And the whole thing can be trained end-to-end with action supervision. We see that this produces efficient skill learning framework for learning this vision-based manipulation policy directly on the physical robot. So this video shows an example. The Viola can solve this complex coffee making task from 50 demonstrations, thus collected within half an hour of time. All right. So now we have the skills from methods like Viola. We then design algorithms to compose them together to solve tasks. So while drawing inspiration from large language model again, so if you think about what's the key mechanism to interact with the language model, is something called prompting. That means we can directly specify the task we want to do in natural language and let the model interpret and execute. So by just asking ourselves, like, can we enable similar interface for a general purpose household robot? What if we ask the robot to bring us a cup of tea? If we want to be more specific, show a picture saying, hey, bring me this cup because this is my favorite. We can show a video demonstration of wiping the floor and ask the robot to imitate to perform the same task. We can even teach the robot new concept in case it doesn't know what a sponge or how it looks like. We show a picture of sponge, say this is a sponge, now use a sponge to clean the table. And we can finally specify further visual constraint, like never enter this room and show a picture of the door. So the central idea is like we introduce Weimar, a generalist robot agent with all this capability. So the reason we can do that is because we unify this different task specification using a new form of multimodal prompt that makes kind of image and text tokens. So this kind of multimodal prompt allows us to express different tasks using the same interface so that we can train one unified model across a broad range of tasks to facilitate zero-shot generalization. And concretely, this Weimar model is an encoder-decoder transformer architecture. It encodes a multimodal prompt with a frozen language model. And for the visual observation, we use object-centric representation, basically representing individual objects as tokens, and just like a Viola. And then when we predict, we select which skill to execute and also the skill parameters and given the prompt and the interaction history. So we investigate how this model scales by training it with a varying size of a training data from 0.1% all the way to the full data set. And we test on different generalization level from level 1 to level 4, where level 3 and level 4 are the hardest because like the robot might encounter novel objects or completely unseen tasks. And we see that compared to the baseline methods, the Weimar achieves more than twice higher success rate on these hardest levels. And in particular for level 4, Weimar trained on 1% of the training data already outperform the model trained on full data sets. And as we increase the data set size and its generalization capability continue to grow. So in our follow-up work, we take this idea of Weimar further to develop a unified interface for human-robot communication. The interface design question has been becoming more and more important in the era of foundation model. So Mutex is a work we present at the conference tomorrow. So it allows us to prompt a multi-task robot manipulation policy with goals and instruction given in text, in audio, in video, in images. By learning across all these different multimodal task specification using a unified policy, that leads to stronger generalization performance across all these modalities. All right, so now we have a set of powerful algorithms. Right, so if you think about algorithms are building a rocket, and then we need the fuel as the data. So for data, we have been developing new mechanisms to generate a massive amount of training data directly from deployment environment, just like the point made by Chelsea earlier. So the central idea here is what I call the robot learning data flywheel. So if you ask me, how much data is enough to train your generalist robot model? I would say it's never going to be enough because the generalist robot in the wild will inevitably encounter new situations it never seen before. Right? So I have to continually collect data and learn in deployment environment. So that gives rise to the concept of a data flywheel that essentially is a virtuous cycle between robot deployment and the model updates. So more training data leads to a better learning model. And better learning model builds a more capable robot. A more capable robots leads to wider deployment of such robotic system. And then in turn, finally, this widespread deployment of a robotic system will create more training data. But to realize this data flywheel, I think there are two fundamental challenges we need to solve. One is, how do we ensure like trustworthy deployment? The robot learning models we have will not be perfect for a long time. So how do we make sure that they don't get into catastrophic failures and in real world situations? The second is, as we deploy these systems in the long term, like so we collect more and more data, how do we develop algorithms to learn efficiently? So we explore these two ideas and in the series framework where we let the robot learn on the job. So here the human and robot collaborate together through shared control. Data from the deployments will goes into a memory storage that used by our algorithm for the updating the robot policy. So the algorithm trains on new policy from the memory storage and deploy back to the robot. So as you can imagine, if we run the system for the long term, as the robot policy improve, the amount of human workload will decrease in the system. So here we illustrate how the series system works in practice. So there are two parallel threads running in this system. Our human robot team can be deployed to perform tasks nonstop in the deployment environment, while in the background thread, the learning algorithm iteratively train the next version of the models on the aggregated data sets. Whenever training is complete, it sends the latest model checkpoints back to the deployment environment and for the next round of deployment. So in this video, it shows an example of a human-robot teaming in this framework. So at the start, the robot runs its policy autonomously. At some point, it gets stuck and asks for help. This is done by our runtime monitoring algorithm. So now this human decides to come in, intervene, and provide action corrections to overcome the bottleneck states. And then the robot takes control again and perform the rest of the tasks autonomously. Right? That gave rise to a data set combines of like human data and also robot autonomous execution. So to train policies in this data, our key idea is to prioritize important samples while discard less useful ones. So we first relabel the states right before the human intervention as the abnormal states because they are the bad behavior we want the policy to avoid. And we then sort the trajectory based on some data curation policy that maximize both the data coverage and data quality. And then we reduce the data set to a fixed size. And by learning on this fixed size data size and improve that learning efficiency will ensure high policy performance. And finally, a sample in the data set, we use some kind of weighting function to determine their importance in the final policy updates. So the entire model is trained with imitation learning objective on these weighted samples. So we visualize like human intervention distribution in this gear insertion task. This is one of the industrial tasks we are interesting. So we see that in round one deployment, here are frequent human intervention as illustrated by the green bars. And as we deploy the system in the long term, in round three, we see that the robot can run autonomously most of the time. So this framework allows us to deploy this imperfect robot learning policy with a human partner and continue to collect data and improve models and over long-term deployment. So that's the algorithm and data part. And then finally, it comes to the hardware. So because the robots are physical systems, so their physical embodiment will determine what they can do at the end of the day. So we have been developing humanoid robots as a human-like generalist hardware platform for robot learning. So this Draco 3 humanoid robot is a multi-year effort with my student Mingyu So and a collaborator at UT Austin, Luis Sintes. So to train our robot at the beginning, we need to figure out how to collect data. So at the beginning of this project, we actually spent a lot of effort to develop a virtual reality-based controller for robot teleoperation. So this video shows the flexibility of this control interface for performing ramen cooking tasks. Now you can crank up the video of sound. Well, you are welcome to visit our lab. So we have robots to make coffee for you in the morning. And in case you're hungry at night, we have robots to cook instant noodle. So Now we have the collected data, right? So we're plugging our skill learning algorithms to learn sensor motor skills. But the one challenge for humanoid robot is that the robot needs to maintain balance while physically interacting with the environment. So we need to kind of devise a dynamic aware real-time whole body controller that translates the kind of task commands to the drawn torque actuation. But this allows us to build a framework that learns this local manipulation skills, both in simulation and also on physical hardware. All right, so I will conclude here. So briefly, I discussed the trinity of building this generalist robot model, the powerful algorithm, massive data sources, and also the versatile human-like hardware. So for algorithms, we are mostly interested in the scaling law, how that apply to robot learning, right? So like, how do we kind of use skill as APIs to scaffold long-term robot behavior, and also through massively multitask training for better generalization. For data, we are interested in focusing on creating a data flywheel so that we can deploy the robots in real-world applications and through human in the loop learning so that it can ensure trustworthy deployments and also let the robots like continually learn in the real world. And finally, for hardware, we start to explore humanoid robots as a generalist robot learning platform to study and develop human-level physical intelligence. So a lot of this work are done by my wonderful students, and I'd like to thank them for their great work, and you will find many of them at this conference. So I'm happy to take questions later. Thank you.